Calculus, you are always awesome, you are always great. So we have done differentiation and we have done differentiation for the single variable and multivariate. So multivariate. What is differentiation? Rate of change is differentiation. Okay. Like I have a ball and the equation of the ball is moving. Ball is moving. So if I see the time, time is zero. Time is 1 second, 2 second, 3 second, 4 second, 5 second. At each time instance, what is the distance? Suppose it is x. Okay. So suppose it is t or okay. So uh, the and displacement and time relationship. So it is suppose that the x-axis is t. So at each time, what is the displacement? Displacement is nothing but x. Function over t is function over t is x. Function over t is x. So x equal to ft. X is the displacement. Okay, so ball is moving. So there is change in x. What is x? X is function over t. If x is function over t, then x equal to t. I mean, this is not God made. So x equal to t means at t equal to 1, x is 1. At t equal to 2, x is 2. At t equal to 3, x is 3. If that is true, then what is dx by dt? Per unit change in time brings how many unit of change in the distance? That is single variable differentiation. So dx by dt equal to 1. So per unit change in time brings 1 unit change in displacement. Dx by dt equal to 1. X equal to ft, function over t. X equal to t. So this is the function. So dx by dt equal to 1. Okay. So if there is one variation in time, there is one variation in displacement. Okay. So fortunately, the function over t is has equation in t, but function over dx by dt has no equation over t. It is constant. If that is true, then what is dx square by dt square? D square x by dt square. D square x by dt square. What is change in change in displacement per unit change in time? D square x by dt square. D by dt over dx by dt. Dx by dt is change in displacement, number of unit of change in displacement per unit change in time. D d dx by dt by dt. Change in dx by dt. Change in dx by dt per unit change in the time. We also call it acceleration. So if dx by dt is velocity, then dt square by dt is acceleration. How much there is a change in velocity per unit change in time? How much the rate of change in displacement changes per unit change in time? This is double differentiation that leads to acceleration. So if x equal to t, then dx by dt equal to 1. So d square x by dt square equal to 0. Because there is no change in rate of change of displacement per unit change in the time. So if time changes, then rate of change in displacement per unit time do not change. So this proves that the first equation, that is x equal to ft function over t, is linear equation. What about fx equal to t square? Okay, so fx equal to t square. then dx by dt equal to 2t. d2x by dt square equal to 2. This proves that there is change in the change rate of change of displacement per unit change in the time. That is d square x by dt square. So if I have change in displacement, how much displacement changes over time, if that amount itself is dependent upon some variable, independent variable, like d square x dx by dt, dx by dt is 2t, means rate of change in displacement per unit change in time again is dependent upon time. At each instance of the time, rate of the change in displacement per unit change in time is again is different. X equal to ft, x equal to t, x equal to t means at if there is a unit change in time, there is some change in displacement. So dx by dt has a value. Okay. Now, if dx by dt is in equation is a kind of in equation with again dependent upon in the form of some independent variable, like if x equal to t square, then dx by dt equal to 2t, then change in displacement, because one unit change in time is again it's a equation over t. So at each time instance, okay, if I take time instance 1, 2, 3, 4, at each time instance, the rate of change that is seen in displacement is different. So at initial moment, the rate of change in displacement means the unit, the displacement unit, okay, how much displacement is changing, because one unit change in time is different around the each time. This is acceleration. Okay, like I'm accelerating my motorbike, I'm accelerating my car, I'm accelerating my horse. Okay, if I'm accelerating, if horse is running, if horse is not accelerating, I'm trying, I'm pulling, but horse is not accelerating. This proves that per unit change in time brings displacement change. Okay, but whatever we are getting rate of change in displacement is not is not kind of it is not in the equation of time. It is constant. Okay, if rate of change of the displacement varies at different time instances, then we can go for another differentiation, d square x by dt square. So how much change in displacement, how much rate of change of displacement varies if there is a variation, if there is a unit change in the time. So at each time instance, so in first go, if we talk about dx by dt, at each time each at each time is instance, the displacement is different. If I go for d square x by dt square, at each time is instance, the rate of change in displacement is different. Okay, at one place the graph value is different. If we draw graph, right? So if I do f ft equal to x, so x is a function over t, then we draw a graph. If graph is changing over the independent variable time, then dx by dt is valid. But if dx by dt versus t, if I draw a graph and again is dx by dt is different at different time, then we have another differentiation. So that comes to acceleration. Okay, like I have a ball. Okay, so I would kind of leave it. Okay, so is the what is the I believe it is the gt square, half gt square or something. Okay, so the displacement is So displacement is directly proportional to if I leave the constant, then it is t square. So displacement at any moment, displacement is t square. If that is true, then dx by dt is 2t. If dx by dt is 2t, then velocity is not constant over the time. At each time instance, dx by dt is different because it is in the variation of t. Okay, so dx by dt is 2t. If I remove the constant, then dx by dt is t. If I differentiate again, then dx by dt is constant. D2 square x by dt square is constant. This proves that I cannot go beyond it. So I can have change in the displacement per unit change in the time and change, and that is called rate, that is called rate of change in displacement, and change in rate of change in displacement over unit change in time. So if I drop the ball, then initially ball is at no velocity, and as ball goes down, then so initially for 1 second, whatever displacement we are getting, then next 1 second, whatever displacement we are getting, next 1 second. So if I move the ball like this, then first 1 second, next 1 second, next 1 second, next 1 second, the displacement is constant. Okay, but if I drop the ball, then first 1 second, next 1 second, next 1 second, displacement is not constant. This proves it. Okay, if that is true, then we have double differentiation. First differentiation tells us that what is change in the displacement per unit change in the time, but that itself is variation with respect to time. It varies. So change in the displacement with the change per unit time is variable with dependent upon the variable t. So dx by dt is proportional to t. D square x by dt square is constant. So initially ball moves slow, faster, 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 faster. When it hits the ground, it is at maximum speed, where full potential energy, whatever the energy from my body, I am transferring energy into the ball. So ball looks still, but it has potential. Like I am very silent, but I have hidden potential. If I come to energy, then energy will be anything. I mean, I don't have that much energy, but I'm saying like that. So now from my body, I'm transferring energy to the ball. The ball has hidden energy. If I leave this ball, then ball start losing the hidden energy that is getting converted to kinetic energy. At the time when it goes near the ground, then the displacement what we see per unit change in the time is high. Then it comes back and it comes to completely rest here. Okay, then full kinetic energy converted to potential energy. If that is the case, whatever the distance we lost because in the friction. So whatever energy it lost in the air and to the air media and to the another media. You can watch my video on E equal to mc square. Okay, so two places it lost the energy. One, it lost the energy in the air media, and another, it lost the energy when it hits the ground, the surface media. Both media, they took the energy. Okay, you can say commission because they are allowing them to pass through. So their commission they took. So energy, air become charged. Okay, ground become charged because of my body energy at the end. Okay, so not only the displacement is varying, the change in the displacement per unit change in time that also varies with the time. So this is dual differentiation. What about multivariable function? If I have a multivariable function, things are changing with two independent variables, d fxy. Okay, I have two independent variables, x and y. Then there is a function over it that is dfxy. If that is dfxy, then how much dfxy, that is z, what is dz by dx and what is dz by dy. Then we call it fxxy and fyxy. If that is true, then what is fxxxy and what is fxyxy and what is fyxxy and what is fyyxy. If that is true, then we can go for more multivariable case and we can go for time dependency. Now, slowly we'll see examples like we have variation in the chord which depend upon the time. So that will proceed further in the multivariate variable case. What is the dual differentiation?